Last time, I know that you enjoyed our video on physics meal, and today you are going to enjoy today's one. Welcome to physics meal. Today on physics meal, we want to look at part 9 of what? Alternating current. And in this part 9, we are considering types of what? AC circuit, part 3. Subscribe to our YouTube channel and make sure that you follow us on what? On Facebook at Mathematics and Science Meal. Let's move together on types of AC circuit. Remember, we have looked at part 1 where we looked at pure resistive circuit. In part 2, we looked at the pure capacitive circuit. And in this part 3, we are going to look at pure inductive circuit. So, number 3, pure inductive circuit. Pure inductive circuit. This is a circuit that contains an inductor as the only source of resistance. So in any AC circuit that we use only inductor to offer resistance, that AC circuit is what? Is a pure inductive circuit. So a pure inductive circuit is like this. This is an inductor. So this is an inductor. This L represents the inductance of the inductor, which is measured in Henry. Remember, if you look at resistance in AC circuit, where we talked about reactance, you remember that I talked about inductance of what? Of an inductor. Okay. So, just like we did in pure resistive circuit, we also in pure capacitive circuit, we are still going to do the same for what? For pure inductive circuit. What and what should we take note of as far as pure inductive circuit is concerned? So in a pure inductive circuit, we need the following. Note the following. 1, the voltage leads the current, or the current lags the voltage by 90 degrees. So the voltage leads the current by 90 degrees, or the current lags the voltage by what? By 90 degrees. So the phase difference is what? 90 degrees. The phase difference is 90 degrees, and we know that 90 degrees is still pi over 2 radians. So 90 degrees, or pi over 2 radians. That's the phase difference. So in a pure inductive circuit, the voltage leads. In a pure resistive circuit, the voltage and the current are in phase. In a pure capacitive circuit, the current leads the voltage by 90 degrees, or pi over 2. But in a pure inductive circuit, the voltage leads the what? Leads the current by what? By 90 degrees. Okay? The third one, the potential difference. The potential difference or voltage is given by, potential difference of voltage is given by VL is equal to IXL. Let's call this equation 3. As a matter of fact, we know that VL now is voltage or potential difference across the inductor. Across the inductor. We know that I is current and XL is inductive reactance. We have defined it before when we looked at reactance, but let's still mention it again. So where this is what? inductive what? Reactance. Inductive reactance. Okay? That's inductive reactance. So the voltage is given by this. So what will be the nature of the phase diagram? The phase diagram. So we looked at number 4. The phase diagram is as shown below. The phase diagram. So, this. This against time, then we'll have this. Okay, so this one is now V, while this is what? This is I. This is the instantaneous voltage, this is the what? The instantaneous current. So you see, in this case now, voltage is leading. If you watch part 8 of our video, part 8 of the video, you will discover that current was leading. That's in a pure capacitive circuit. And in the phase diagram, this was the current, while this one was the voltage. But now the voltage is leading. You see that? So the phase difference between them is actually 90 degrees, 0 degrees, 90 degrees. So the phase difference is 90 degrees, also in a pure inductive what? Inductive circuit. Now, I also talked about two equations. Here now, the current is going to be I naught sine what? Omega t. For voltage will be V naught cos omega t. Yeah, that's what it's going to be. The voltage will be V naught cos omega t. Current will be this. Remember, I say alternatively, we can write this as V is equal to V naught sine, if I want to write 90 plus omega t, right? Remember this. Yeah, you can write it like this. But you know, people will be relatively confused with this. I was trying to explain the trigonometry ratio implication of that using complementary angles in our previous video. So if it is still not clear, you can just leave a comment both in that previous video and also in this video, so that I can actually run a little video to clarify you on complementary angles. Complementary angles in trigonometry what? In trigonometry ratio. Okay. So that's the phase and the phase difference, or the phase diagram rather, the phase diagram for a pure inductive circuit. Now, what will be the vector diagram? The vector diagram. The vector diagram, point number 5. The vector diagram is as shown below also. So the vector diagram is like this. We have our VC in volts and our current in ampere. So this 90 degrees. The voltage is now leading. You remember that in pure capacitive circuit where current led, you see we turned this. This was down here. The voltage was in the negative what? Negative y-axis, right? Showing that the voltage was lagging, or that the current was actually leading. So the slope of this graph, if maybe you plot the graph of V against what? Against I, right? You are going to have a straight line graph in this form, and the slope of that graph will be equal to the what? Inductive what? Reactance. Yeah, it is going to be inductive reactance. So in the graph of V C against what? I, going to have the slope which will be equal to the inductive reactance. So point number 6, the impedance is equal to the inductive reactance. So that means Z is actually equals to XL for a pure what? For a pure inductive what? Inductive circuit. Right? Should we make more points? Yes, I think we have to. So let's also note, having looked at this and looked at this, let us also note that the power factor in this case now is going to be what? 0. The power factor will be 0 in this case. The power factor will be 0. So power factor is equal to 0. The power factor is equal to 0. So in this case, energy is stored in the magnetic field. So the significance of energy in the three circuits differ. Now we saw that in a pure resistive circuit, that energy is dissipated as heat, right? Energy is dissipated as heat. That's in a pure resistive circuit. Now, when you looked at the pure capacitive circuit, we saw that energy is stored in what? Electric field. And then in a pure inductive circuit, energy storage is in the what? In the magnetic field, as a result of the inductance of the what? Inductor. The storage in the electric field as a result of what? The capacitance of the capacitor. The dissipation of heat in pure resistive circuit is as a result of the resistance of the resistor. Okay, so that's all on pure inductive circuit. In our next video, we'll start looking at the combinations of components in order to generate more circuits. For example, we have resistive inductive circuit. We also have resistive capacitive circuit. We also have resistive inductive capacitive circuit. I love the way the names are sounding. Resistive inductive capacitive circuit. Resistive capacitive inductive circuit. Resistive inductive capacitive circuit. As if someone is trying to actually sing a song. Alright. But that will be in our next class. Make sure that you continue to watch our videos and make sure that you follow us for more. Also, tell your friends about this particular video because it's going to benefit them. My name still remains Engineer Ike Ogechukwu. Permit me to take water. Alright, remember that I love you, even if you forget any other thing. Goodbye.